In today's video, we're going to carry out a practical session, a physics experiment. So every experiment has got a title. So title of the experiment, In this experiment, we will be required to investigate the relationship between the period T of a spring system and mass m loaded on it, and mass m loaded on it. That is the title of the experiment. So we're going to conduct a practical session in physics. In physics, we carry out experimental investigation. So in this experiment, you will be required to investigate the relationship between the period T of a spring system and mass m loaded on it. So the experimental setup, let's consider the experimental setup. So this is the experimental setup, how the apparatus are set up. This is the mass M, loaded, then this is the spring. This is the stand and the clamp spring mass loaded on it. So we're going to set up this apparatus to carry out our investigation. So one of the instruction number 1 says suspend M on the spring as shown. Suspend M on the spring as shown. So this is the first instruction that we have to follow. So this is the experimental setup. So I'm going to set up the setup. This is the stand and the clamp. This is I've done the experimental setup. Can you see it? This is the experimental setup as shown there. Right, now let's follow, when I'm carrying out an experiment, it is very vital to follow all the basic instructions in that experiment so that you successfully conduct your investigation or your experiment. Right, let's look at the following set of instructions. The following set of instructions: further instructions. Set M into vertical oscillations of small amplitude. 1. Set M into vertical oscillations of small amplitudes small amplitude. So this will be oscillating this vertical plane, and so can you see? So it means we're going to set our oscillations in a vertical plane. In fact, our oscillations are going to be vertical, in a vertical plane. Instruction 2, make measurements to determine T for this mass M. Make measurements to determine T. T is the period time for uncomplete oscillation for this mass M. So this will guide us into setting up a table of results for this experiment. Then instruction. So we'll set up we'll use this to come up with a table of results. So it means in our table of results we'll have something like this. We'll have M in grams. In order to measure time for one complete oscillation, we measure first of all we measure time for a certain number of oscillations. So we measure time for 10 T1 oscillations, 10 T2 oscillations, then we should have an average. Then we finally have our T. This is how we should set up our table. So it means one of the columns is going to have a column for mass. Because this mass M is 100 grams, right? Then we should measure time for 10 oscillations for the first instant, time for 10 oscillations for the second instant. So we repeat to minimize random error. Then we average, right? Then we divide by 10 to get the time for 10 oscillations, right? We'll do that as we proceed. So this is basically how part of the table will appear. Then the other instruction. Let's look at another instruction. The other instruction says repeat the measurements of T up to 6 readings for various values of M. For various values of M up to 0.6 kg or 600 grams. So it means we should expand our table and put all the sets of readings that are required in the table. Then the final instruction says, include a column of T squared in your table of results. In your table of include a column of T squared. So I've proved that. So after having done our experimental setup, now we've got an idea of how our table should be like. So then we know that we should have M up to 600 grams. Now our next step is to have a complete table of results. Then we are going to check this. We are going to collect raw ratings. Our next task is to have a complete table of results. So this is going to be our table of results. This is what is called raw data. So our table is going to have M in grams. It should be complete. 10 T1. We are going to measure 10 oscillations for the first time, then repeat, then average. So this is in seconds. This is in seconds, this is in grams, and this is in seconds. Then we'll have T there, then we'll have T squared. Let me read so that all the values, we'll have M there, T1, T2, so this is in seconds, then we have our T there, then we have our T squared. This is in seconds, this is in seconds squared. So it means our M is from 100 grams, 200, 300, 400, 500, 200 there, 300 there, 400 there, 500 there, then 600 there. Here we are. So all the sets of ratings will be within this table. So if you have a complete so quickly measure time for 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 4,19, 400 grams. Then we'll redo again. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let me repeat it. 0, 1, 2, 3, 4, 5, 6, 8, 9, 10. 4,34. Can you repeat for 200 grams? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 6,16. You redo it again. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 6,19. Move on to 300. You have to do it very fast. Physics should be able to manage time. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 7,47. Right? Okay. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 7,38. Move on to 400 grams. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 8,59. Again. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 8,57. Then we move on to 500 grams. Right, this is our 500 grams. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9,65. And move on to, again we repeat, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9,62. Then lastly, we will do for 600 grams. Lastly, we will do for 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10,47. Another set, another 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10,63. Means now we've got all the 6 sets of readings, right? We've managed to come up with the complete table. So we'll have to average this 4,19 plus 4,34. What do you get? Divided by 2. You get 4,265. Right? 6,16 plus 6,19. 6,175. 7,47 plus 7,38. 7,425. 8,59 plus 8,57 divided by 2. 8,58. 9,65 plus 9,62. 9,635. Then here we divide by 10 to get the time, the period. 0,4265, 0,6175, 0,7425, 0,8580, 0,9635, 1,055. Right. Then we have to square there. 0,4265 squared. We get 0,1819. 0,6175 squared. 0,3813. 0,7425 squared. 0,5513. 0,8580 squared. 0,7362. 0,9635 squared. 0,9283. 0,9283. 1,055 squared. 1,1130. Right. So we can to verify that these values are correct. Right? 4,19 plus 4,34 divided by 2. This is correct. Divided by 10. This is correct. Squared. This is correct. 6,16 plus 6,19 divided by 2. This is correct. Divided by 10. This is correct. 10 squared. 0,3813. Correct. Right? 7,47 plus 7,38 divided by 2. This is correct. Divided by 10. This is correct. Then we square. This is correct. Then 8,59 plus 8,57 divided by 2. This is correct. Divided by 10. This is correct. 0,8580. Then squared. 0,8580. Then we square. 0,7362. This is correct. Then 9,65 plus 9,62 divided by 2. 9,635. This is correct. Divided by 10. This is correct. We square. This is also correct. Then 10,47 plus 10,55 divided by 2. 10,47 plus 10,63 divided by 2. Got 10,55 divided by 10. Get 1,0550 squared. 1,055 squared. 1,1130. Right. So this is what we got. This is what we should obtain. So the table of results. The table of results must be complete. Must have correct row readings. Must have all the columns. All the columns must be headed. You see, we have headed all the columns. All the columns are there. All the row readings are correct. This is a complete table. So we should have a complete table. Now moving on to we're moving on to something else. Something else is different. But we should quickly have m against t squared. We should have m against t squared, which is 0,1819, 0,3813, 300, 0,5513, 300, 0,5513, 400, 0,7362, 500, 0,9283, 600, 1,1130. So now I've demonstrated how we should come up with a complete table. It is very, very vital for you to have a complete table. Now the next thing, after having had a complete table, what is now very important is to have processed the data. Now moving on to, so because this is raw data, so I'm moving on to process the data. According to theory of this experiment, from processing of raw data, according to the theory of the experiment, for any spring system, T is equals to 2 pi m over k, where m is the oscillating mass and k is the spring constant. So, question, plot a graph of t squared against the m. So we're going to plot a graph of t squared against the m. We're going to plot a graph. Let me get a graph. We're going to plot a graph of t squared against the m. I'll demonstrate to you how a graph is plotted. Why are we plotting a graph of t squared against the m? It's very simple. This is because the reason why I'm plotting a graph of t squared against m is we've been told that t is equal to 2 pi m over k, right? So we square this and that, so it will be t squared is equal to 4 pi squared m over k. So we're going to plot a graph of t squared against the m. So this means t squared is going to be 4 pi squared over k m, where t squared will represent y-axis, and this will represent the gradient, and this m will represent the x-value. So this will be a straight line graph, right? This is going to be a straight line graph. Remember, in our table of results, so when plotting t squared against m, we go back to the table of results. When plotting t squared against m, we go back to the table, but I'm only going to take values for m and values for t squared. What you got in the experiment. 800 grams, the corresponding t squared is 0,1819. At 200 grams, it's 0,3813. At 300 grams, it's 0,5513. 500 grams is 0.9283. At 600 grams, it's 1.1130. So plot a graph of t squared against m. So how do you plot our graph of t squared against m? It's very, very, very simple. It's very simple. So when plotting a graph, what we do, so want to plot a graph of t squared. So we have to have an axis of t squared in seconds, right? M is in grams there. So m is from 100 to 600. So we can have a false origin. So this will be our false origin. So this will be 100, 200, 300, 400, 500, 600. Right? So this is 100, 200, 3, 4, 5, 6. So it's a uniform scale, horizontal. It should be more than half the axis, the horizontal axis. Then t squared is varying from 0.18 to 1.113. So it will be 0.1, 0.2, 0.3, 0.4, 0.5. So this is a false origin. So it's 100, 200 for the x, for the horizontal axis for m. Then 0.1, 0.2, 0.3, 0.4 up to 1.14 for t squared. So it should go up to 1.2. It should go up to 1.2. So from there, 0.1 to 0.2, so it's uniform. Means 0.11, 1 to 1.9 up to 0.2. So it should be a uniform scale. So I'm going to plot all the points. So for 100, it's 0.18. 0, for 200, 0.38. For 300, 0.55. For 400, 0.74. I've rounded up. For 500, 0.93. For 600, it's 1,11. So 1,11. So I've plotted all the points. So it is important to plot all the points correctly. So for 100, 0,18. For 200, 0,38. So should have a convenience scale for t squared, a convenience scale for m. Then I'm going to plot a line of best fit. I'm going to draw a line of best fit there. This is the line of best fit. There are 2 points that side, there are also 2 points that side, so it is balancing this card. So I'll read off points along the straight line graph. So I read off 2 points, which is 100, 0,15 and 531. They are 100. So these points, they are very vital. So we are going to use these points to calculate the gradient of the graph, right? So this is the graph, t squared against m. The horizontal axis is more than half the scale, the vertical axis is more than half. This is the line of best fit. I have plotted all the points. So now the next question is, so I've plotted the graph of t squared against m. I've plotted the graph of t squared against m. Now what should follow now is calculate the gradient of the graph. The next step is to calculate the gradient of the graph. Calculate the gradient of the graph. So we use these 2 points that we have read for this point and that point. So we'll say 100 is x1, 0,15 y1. Another point is 530 grams, 1, which is x2, y2. So gradient is going to be equal to y1 minus y2 over x2 minus x1, which is 0,15 minus 1 over, this is x1 minus x2, sorry, 100 minus 530. So the gradient also is unit. The gradient is unit. So if you calculate very well there, you should get 0,15 minus 1 divided by 100 minus 530, which is 1,98 times 10 to the power minus 3. The answer is 1,98 times 10 to the power minus 3 seconds squared per gram. Remember, this is in seconds squared. This is in grams. So the units for gram are seconds squared per gram. That is the gradient. So it is vital also to add the units of the gradient. The next question is deduce. The last equation is from this equation of t is equals to 2 pi. Deduce the value of k. So t squared, agree that t squared is 4 pi squared m over k, and we plotted y against the, is to say for t squared is equal to 4 pi squared over k m. M is this, y is t squared, x is represented by m. So m, so we use our gradient to calculate k. So m from t squared is equals to 4 pi squared over k m. So we said y is equals to mx. So gradient is equals to 4 pi squared over k, or m is equals to 4 pi squared over k. So we'll use our gradient to deduce the value of m. What is the value of the gradient there? Remember, we said we have created our gradient. We said gradient is equal to 1,98 times 10 to the power minus 3 seconds squared per gram. So I say 1,98 times 10 to the power minus 3 is going to be 4 pi squared over k. So k is going to be 4 pi squared over 1,98 times 10 to the power minus 3. That is finally the value of k. So we can calculate k and its units. We can calculate k and its units. So remember, now k and its units this will be equal to, let's count it together, 4 second function pi squared divided by 1,98, that's 1 minus 3. We should get 19,938,6. This will be going to be grams per second squared. This is going to be the value of k, right? You can express k in kilogram per second squared, which is also fine. You divide by 9 by 1,000. No problem. So this is how basically an experiment is done. You start by experimental setup, you do your table of results, make sure your table of results is complete. When it is complete, then you plot a necessary graph, make sure both axes are labeled, convenience scale. Also do your analysis correctly, have a line of best fit. Those basically are the skills that are required when doing an experiment in physics. We repeated the values for 10 for 10t, for the number for 10 oscillations to minimize random error. So as you go, we'll do more experiments so that you gain more skills in doing your practice.